Okay. Hello, so I am Jonathan Freundlich, and I'm currently working at the Paris Observatory with Françoise Combe. I will soon join Avishai Deckel's team in Jerusalem. So in the previous talk, Aaron presented a model in which global inflows and violent outflows were the main drivers of the cusp-core transformation. Here, I would like to present an alternative theoretical model we developed with Amrel Zant from the British University in Egypt, in which core formation occurs through a diffusion process akin to two-body relaxation, as in stellar dynamics. So in this model, we're trying to describe from first principles how gas density fluctuations arising from different feedback processes can affect the trajectories of dark matter particles, produce a core, and hence help solve some of the challenges of the lambda CDM model. So I'm not going to go into the details of this. So I listed some of these challenges at galactic scales, and what I'm focusing here is the core cusp discrepancy, as was already evoked many times today, which is the fact that dark matter-only simulations predict relatively universal profiles for dark matter halos that are relatively peak toward the center, while observations seem to imply a much more shallower density profile. So in order to solve this discrepancy, there are basically two kinds of approach, either solutions that fundamentally change the physics of the cosmological model, and James Bullock notably talked about self-interacting dark matter models today, and on the other hand, models that would invoke baryonic processes within the lambda CDM framework. So this is notably relatively important also because baryons play an important role precisely at the scale where these problems arise, that feedback processes and outflows are extremely important in galaxies, and moreover, some hydrodynamical simulations with different feedback implementations were able to reproduce core density profiles. But the thing is that sometimes these simulations are relatively complex, and it's not always easy to say what is the specific mechanism that is at stake for this cusp-core transformation. So because dark matter mostly interacts gravitationally, it is through the gravitational force that baryons can affect dark matter particles, and that can be either due to adiabatic contraction, dynamical friction, or probably more importantly, repeated potential fluctuations from feedback processes. And that was notably developed by Andrew Ponzen and Fabio Governato in 2012. And in these two plots from their simulations, you can see the mass fluctuations average at different radii, which means potential fluctuations, and the corresponding effect on the dark matter particles. So this is the mean radial orbit of these dark matter particles as a function of time, and they slowly drift away from the center, leading to the formation of a core. So in this work, they have a specific implementation of feedback that lead to these mass fluctuations. And so what we wanted to do with Amrel Zant was to try to have an a priori theoretical model that would enable to explain core formation in this context. So what we assume is that we have stochastic density fluctuations in the gas field in the inner part of the halo that will change the potential and then hence affect the dark matter particles. So our basic assumption is that we have an imparted homogeneous gaseous medium in the halo, which is obviously an assumption that can be discussed. We assume that we have isotropic density perturbations within the inner part of the halo. We describe these fluctuations by a power law power spectrum so which is motivated by the fact that there could be a turbulent cascade from an energy driving scale, which can be the outflows or the bubbles due to the feedback, different feedback processes, down to a dissipation scale at much lower scale. So we, for the sake of the calculation, we assume cutoff scales for this power spectrum, and we assume that this process is continuous. So in more details, we decompose the density contrast delta in terms of its Fourier component, and we consider that each Fourier mode, delta of k, induces a small kick on the dark matter particles. So all of these small kicks cumulatively induce the dark matter particles to deviate from their original orbits, and we express the deviation in velocity in terms of the force autocorrelation functions that we calculated under our assumptions. And so in the diffusion limit, that is in the limit where the perturbation, the size of the perturbation is small compared to the distance traveled by the dark matter particles, we are able to obtain analytically a relaxation time, which is set by the largest fluctuation scale and primarily depends on the fluctuation level and on the gas fraction. So we evaluate this relaxation time in the case of a fiducial dwarf galaxy, so which corresponds roughly to the kind of galaxies where we are able to observe this kind of phenomena. But the thing is that the relaxation time gives us a time scale at which these perturbations are expected to affect the dark matter particles, but does not necessarily tell us what is the global response of the system. So in order to do that, we carried out relatively simple numerical simulations with the self-consistent field method developed by Hernquist and Ostreicher. We put an initial NFW halo. We implement the perturbations as in our analytical calculations and as in our model, and we evolve the simulations. And so in a first set of simulation, we follow relatively closely the assumptions of our calculations by imposing spherical symmetry or isotropy on the system. And what we observe is that we do observe the formation of a core within a time scale that is coherent with the relaxation time that we had calculated earlier. The parameterization of the core mostly depends on the fluctuation level and the gas fraction, again, as in our calculations with relatively weak dependence in the power law index, and the fact that the cutoff that we assumed do not affect the resulting core. So that was, as in a first step, by assuming a spherical symmetry in our system, imposing spherical symmetry. So if, on the contrary, we do not impose spherical symmetry, then what we observed is exactly the same effect with the same parameterization, so which kind of give us confidence on the model, but everything happening at a much faster time scale. And so it seems that asphericity, or the non-isotropy of the system, is a key ingredient for the efficiency of cusp-core transformation. And that was the object of also a paper by Andrew Ponson in 2015. And so it seems that the processes that redistribute the energy from the baryons to the rest of the halo might be channeled in part by non-isotropic processes, and which probably is different than in the model that was just proposed by Aaron Dutton, in which there is spherical symmetry. So to conclude, in our model, we have developed this model that relies on a diffusion approximation and that describe core formation from stochastic density perturbations. And so in the next stage, we would use hydrodynamical simulations to better characterize the statistical properties of these density fluctuations. And hopefully, if as we have a relatively simple parameterization of the relaxation time, we hope that this could also in turn help better understand the effects of different feedback implementations on the cusp-core transformation. So, as I already mentioned, there are different descriptions of this process, notably that by Aaron Dutton and Avishai Deckel, which it would be interesting to compare both approaches. And there is another approach that is currently being submitted by Jean-Baptiste Fouvry and Rebecca Brieri that also try to describe this process as a diffusion process. Finally, there could be some generalization of our calculation. And I think that to finish with, the fact that that isotropy is a very important aspect of the cusp-core transformation that needs to be studied in more detail.
Okay, questions for Jonathan? Starting here with James.
How sensitive are things to lambda min?
To lambda?
To lambda min, the smallest scale where you truncate things.
Yes, so it's actually highly, it doesn't depend that much on lambda min. So there is a dependence in lambda max, but the thing is that the depletion time depends only on lambda max. So it's as if basically the large scales are sweeping the smaller scales, and that the smaller scales are disappearing in the effect of the larger scales. And the thing is that although the relaxation time depends on lambda max, the effect on the core is independent of lambda max. And that we can we can understand it in terms of diffusion limit, in the sense that the time scales, so basically we assume a different number of kicks, and the force for each kick will depend on lambda max, but basically there are different things that compensate each other, and that makes that the effect on the core in the end doesn't depend on lambda max.
So if you injected all of the energy, let's say in a ring, rather than at the center or something like that, would you get a very different result, do you think? I mean, maybe that's a related, I mean, it's not the same question, but it's potentially related here in terms of where the energy is injected.
So, I mean, we haven't done such simulations. Here we basically assume that the energy is injected in a small sphere at the center. And
it might be interesting. I mean, I think the self-consistent field code should give you the possibility to look at where, you know, whether this depends strongly on where the energy is injected, which could be useful.
It should be easy to implement, actually.
Okay, any last questions for Jonathan here? If not, let's thank him again for a nice talk.